A GPC analysis should obtain the most significant information on molar mass distribution. Let's take a look at 3 different resins. We will start with the simplest structure, polyethylene homopolymer. Determining the molar mass distribution of this polyethylene resin as represented here is very simple. Any high-temperature GPC with a concentration detector will provide the molar mass distribution of these types of resins. For illustration purposes, this is what an extended chain of the homopolymer molecule would look like in 5-unit lengths and also in coil formation. The separation mechanism of gel permeation chromatography is implemented by passing the sample through a column filled with a porous packing material. The large molecules are excluded from most pore sizes and travel faster through the column. As the molecules decrease in size, they go through more pore sizes and are eluted later. At the end of the process, we obtain a full molar mass distribution curve, which unequivocally characterizes the microstructure of this resin. In this case, with proper calibration, any concentration detector, whether refractive index, infrared, or evaporative light scattering, are all capable of monitoring the polymer concentration as the sample exits the column and thus obtain the MMD. What happens if a comonomer is incorporated into the linear polyethylene chains? The simplest structures are polyethylene copolymers that are produced in single-site catalysts. In this example, we can see the molecule of an ethylene butene copolymer. To characterize this type of resin, in addition to the molar mass distribution curve, we need to know the amount of comonomer added and how it is incorporated. Or in other words, the number of short chain branches in the molecules, along with the molar mass distribution. In this depiction, we see that all molecules have the same number of branches per unit length. This is usually expressed as number of methyls over 1,000 carbons. But how do we measure the presence of these branches in the molecule chains? For this, we need a detector that measures concentration as well as composition for each molar mass fraction. An infrared detector can simultaneously monitor the absorbance at various wavelengths. So in this case, we can use one wavelength to measure concentration as total CH, and the other one to measure composition by measuring the number of methyls in every chain size fraction. The GPC separation mechanism is the same, but thanks to the infrared detector, 2 signals can be obtained instead of 1. The concentration signal shows in this case a narrow molar mass distribution, typical of a single-site catalyst resin, but a second signal related to composition is also captured, responding to the presence of methyl groups. The ratio of the 2 curves is proportional to the number of methyls per 1,000 carbons. Once the detector is calibrated, we can get the number of methyls corresponding to the short chain branches. And in the case of single-site catalyst resins, it is uniform along the molar mass. Aside from the distribution composition, the average comonomer content can be obtained as a ratio of the area of methyl signal over concentration signal. What if the comonomer is not uniformly incorporated across the molar mass distribution? Although this molecule may look the same as the one produced in the single-site catalyst, they are different because in this case, the presence of ramifications per unit length is not uniform. These types of resins, where the number of branches per unit length increases as the molar mass decreases, are produced in multi-site catalysts, and molar mass distribution alone is not enough for their full characterization. Composition is required. With linear low-density polyethylenes, we see that, when performing the GPC analysis with the same infrared detector as before, we simultaneously obtain the concentration and composition signals. And when calculating the ratio of the two curves, we find that for this LLDPE, the number of branches decreases as molar mass increases. The infrared detector is the only detector capable of obtaining both signals simultaneously, telling similar products apart. This information is crucial, especially with the production of complex polyolefins in multi-catalyst processes becoming more prevalent in the industry. There are resins with similar molar mass and the same total amount of comonomer incorporated, but with different composition dependence along the molar mass. This is a polyethylene copolymer of high density used in pipe applications. The molar mass distribution discriminates two peaks, usually obtained in two separate reactors. We observe the presence of a small number of branches increasing with the molar mass, a microstructure in demand for this product's applications. However, there can be polyethylene resins with similar broad distributions also produced in two reactors, but with completely different performances. In this case, the short chain branching is incorporated in an opposite manner, decreasing the number of branches as molar mass increases. Another example is the case of ethylene-propylene copolymers. Ethylene content can be obtained by the reduction of methyls per 1,000 total carbons, giving us the opportunity to determine ethylene weight percentage. These EP copolymers were produced in the same process, but in three different catalyst and reactor conditions. The molar mass distribution is nearly the same on all three cases. However, the ethylene incorporation along the molar mass results in three different composition curves: homogeneous along with the molar mass, increasing ethylene incorporation, and decreasing ethylene incorporation with the molar mass. The three samples have almost the same molar mass distribution, but the properties and performances are completely different. The GPC analysis of polyolefin homopolymers only requires the concentration signal, which can be obtained through different detectors. However, a complete characterization, that is, a full GPC analysis of polyolefin copolymers, requires the additional short-chain branching information, and this is only available through infrared detection. The infrared detector has been extensively used for concentration and chemical composition to obtain molar mass distribution and short-chain branching information in ethylene alpha-olefin and in ethylene propylene copolymers. But recent advances have led to a new high-performance filter-based infrared detector that extends the spectral range up to the carbonyl band and beyond. The number of simultaneously detected available bands has also been increased up to 6, which opens the door to the development of new specialized applications. GPC-IR is the only high-temperature system that integrates infrared detection capable of measuring molecular weight distribution and short-chain branching along the molar mass in polyolefins at the same time.